Okay, so so I'm very happy to introduce for this quantum seminar Abhishek Agarwal, and he will be speaking to us today about modeling non-Markovian noise in driven superconducting qubits. So before handing over to you, Abhishek, I'll just quickly read your bio. So Abhishek Agarwal is a higher scientist at the National Physical Laboratory in the UK. He graduated with a degree in physics and philosophy from the University of Oxford in 2020, and since has been working at the NPL, National Physical Laboratory. His research interests include modeling noise in quantum computers and developing quantum algorithms for material simulation. So thank you for agreeing to give this seminar today. So I'll hand over to you now.
Thanks for the introduction, Graham, and thanks for the invitation. Let me try sharing my screen. Can you see the screen okay?
Yeah, we can see.
Okay, perfect. So like I said, my name is Abhishek, and I'll be presenting some of our team's recent work on modeling non-Markovian noise in superconducting qubits. I'll begin by just giving a very quick introduction to NPL and my group, in case you haven't heard of us. So at the National Physical Laboratory, we are the UK's National Measurement Institute. And what that means is that we're responsible for developing and maintaining the primary standards in the UK, and also multidisciplinary research and development relating to benchmarks and standards and everything relating to testing and measurement. In our team specifically, so I'm from the quantum software and modeling team. We work on 3 strands. So the first is developing quantum algorithms. So for example, we have a few papers on developing algorithms for material simulations on quantum computers. The second strand is modeling noise in quantum computers that we have today. So that's the work that I'll be presenting you today. And we also, having these noise models, we can also see what the effect of the noise is when we're actually running quantum algorithms. And the third strand is using and developing machine learning techniques to scale up the characterization and calibration of quantum technologies in general. So for example, using machine learning for qubit calibration, let's say. And we collaborate with quite a few companies in the UK as well as universities, and we're always looking to collaborate more widely. Okay, let me now give you a quick outline of the structure of this talk. So I'll begin by motivating why we're interested in modeling noise. Then I'll talk about the noise that we have in superconducting qubits available today. Then I'll describe the method that we have developed for characterization of this noise. And then finally, I'll present some of our results for the idle and the driven qubit. Okay, so why are we interested in modeling noise? As you may well know, the qubits that we have available today are very noisy. And that's one of the main limitations in the number of qubits and the noise present in them today is the main limitation in the advantage, in getting an advantage out of using quantum computers. And by modeling the noise in the quantum computer, it allows us to learn about the sources of errors that are present. So if you know about what's causing a particular error, you can then try to mitigate it. It allows improving qubit calibration. It allows developing method for mitigation of the noise, and also allows us to estimate the confidence that we can have in the results that we obtain. Now, there's various existing methods for characterization of noise, but a lot of them focus on what's called Markovian noise. And I'll come back to what that means in this context in a bit. But existing methods for the characterization of non-Markovian noise are quite expensive in terms of the number of circuits that we're supposed to run. So that's why there's need for developing new methods and having models for non-Markovian noise so that we can understand the effects on superconducting qubits. Okay, so where do we begin? So what kind of noise can we have in the quantum computer? I'll mention that in this work, we're focused on just single qubit noise. So the noise that you would have, even if you just had a single qubit. And the first step in understanding the noise might be looking at, okay, even if I'm not doing anything on the qubit, I'm just leaving it idle. Is there any noise? Is anything happening to the qubit even when I'm not doing anything? Now, one way you can evaluate whether there is such noise is that you can prepare the qubit in some initial state. You can then let it evolve idly, which essentially just means wait and do nothing. And then you can measure the qubit and look at what its state was. Now, ideally, if you don't have any noise, the qubit state will remain unchanged. So when you measure it after waiting, it'll be the same as the state that it was when you prepared it. But if you have certain kinds of noise, the qubit won't be in the same state. And I'll give you some examples of what kinds of noise we can expect to have. So the first one is what we're calling a phase error, which essentially is a sigma z term in the Hamiltonian of the qubit. Let me bring the pointer up. Yeah, so you can see here that we have an additional sigma z term in the qubit Hamiltonian. And what that leads to is that the qubit state on the Bloch sphere, which is shown here, oscillates about the z-axis. Now, physically, this can be caused, for example, if you haven't calibrated your qubit frequency correctly. And in that case, you always have this extra term in the Hamiltonian. A second kind of noise you can have is called dephasing noise. The physical reason is, for example, if you have very rapid fluctuations of your qubit frequency, effectively that shows up as a random noise, which makes the qubit state go towards the z-axis, as shown here. And a third kind of noise can be amplitude damping. So generally, in superconducting qubits, the one state corresponds to a high energy state than the zero state, which is why at each point in time, there's a certain probability that you will decay from the higher energy states, so the one state, to the zero state. So on the Bloch sphere, this effectively means that the qubit state slowly points towards the zero state. These three noises together form what we're calling the Markovian model. And we will use this to compare against other noise models that I'll show you later. And just to show you that if we combine these three kinds of noise, together what we get in general is a damped oscillation in the qubit trajectory in the Bloch sphere, as you can see here. But that's not the only, those are not the only sources of noise you can have. So what I mentioned were idle qubit errors, but you'll also obviously have errors when you are actually applying operations. So when you're applying gates on the qubits, you may not have calibrated the gate perfectly, and you can have over or under rotation errors, or your rotation axis may not be correct, or your gate can introduce other kinds of errors, such as phase errors that I mentioned. And even some more kinds of noise can be state preparation and measurement errors. So when you prepare a qubit in a particular state, or when you're measuring the qubit state, there'll be some inaccuracy in that process, and that constitutes the state preparation and measurement, or SPAM error. And there's also leakage to high levels. So generally, superconducting qubits, you don't just have the zero and the one state, there's higher energy states as well, which ideally you want to avoid, but because of noise, you may actually leak onto these high energy states. In this work, we're ignoring the latter two kinds of errors. I'll come back to why we're doing that in a bit. I mentioned Markovian and non-Markovian a couple of times. So what does that mean in this context? There's also different ways of defining Markovianity, and I won't get into the many different ways of doing that. But for our purposes here, if we can model the environment that the qubit interacts with as being memoryless, we have what we call Markovian noise. And as I showed you before with the Markovian model, we typically get single frequency oscillations as a function of time. So this is, for example, with idle qubits. If we measure some qubit observable after waiting different amounts of times, typically we get single frequency damped oscillations. On the other hand, if you cannot model the environment as being memoryless, then we obtain non-Markovian noise. And this has two interesting signatures. So firstly, we can now have multi-frequency oscillations of qubit observables, but we can also have qubit purity oscillations. So the purity measures how pure the qubit state is. And typically, over time, because of noise, the purity reduces, although there's some kinds of noise that also lead to the purity increasing. But because of non-Markovian noise, you can actually have the qubit purity oscillating. So the qubit initially, let's say, is in a perfectly pure state. It then goes through a maximally mixed state, and then back to being a pure state, and so on. So these are two signatures that you can use to detect whether or not you have a Markovian or non-Markovian noise. So how do we begin to try to model this kind of noise? So the first noise model, non-Markovian noise model that I'll show you, involves letting the qubit interact with another quantum system, which we can model as another two-level system. So in the schematic shown here, so we have the qubit, and because of Markovian noise such as dephasing and amplitude damping, there's the interaction with the environment or the bus that leads to decoherence. But now we also add this two-level system that the qubit interacts with. So the form of the interaction is shown here. So the first term is just the phase error term in the qubit Hamiltonian. And the second term, we have a sigma zero operation on the qubit and a Pauli X operation on the two-level system. And this interaction between the qubit and TLS leads to non-Markovian noise. The strength of this interaction is governed by the parameter mu here, which I'll use in the later slides as well. Now, the reason why we get non-Markovian noise is because we only look at the qubit subspace. So effectively, we're tracing out the two-level system and we obtain non-Markovian noise. If we were looking at the entire system, we're still only considering Markovian noise. Now, the reason why we're interested in a model like this is that physically in superconducting qubits, you actually have these two-level systems that the qubit interacts with. The reason for those can be, for example, if you have molecules stuck to the qubit surface, or you can have atoms which can be in, for example, multiple configurations. So you can approximate these physical issues as two-level systems, and the qubit can then interact with them. So that's the physical motivation behind such a noise model. We also used a second kind of model to take into account non-Markovian noise. And this one uses what's called the post-Markovian master equation. So the master equation is shown here. So the first term that we have corresponds to the Markovian noise. So here, L is the Lindbladian operator. And if you only had Markovian noise, this is the master equation that you would use. But now to introduce non-Markovian noise, we can integrate over the past times, and the weightage is given by a memory kernel. And this integration over past times effectively introduces non-Markovian behavior. Inspired from previous papers, we choose the Lindbladian operator here, which leads to the non-Markovian noise, as being the dephasing operator. So effectively, with this model, we have the Markovian model with the addition of a non-Markovian dephasing operation. The memory kernel can take is almost an ansatz, and you can choose the form of the memory kernel. In this work here, we've just chosen the simplest memory kernel, in which we only have an exponentially decaying kernel. So I've shown you two different noise models, but actually in our recent paper, we found that we can relate the parameters of these two noise models directly. So in terms of the results, we expect to get very similar results just because of the fact that we can relate the parameters of these two noise models. So the parameters that we have are the phase error. So that's the delta omega term that I mentioned. We have qubit dephasing, which corresponds to the gamma d term here. We have amplitude damping, which is shown here. And these three parameters are the same in all three noise models: so the Markovian one, the qubit-TLS one, and the post-Markovian master equation model. In the qubit-TLS model, we have the addition of the parameter mu, which governs the interaction strength between the qubit and the TLS. And in the post-Markovian master equation, we have two additional parameters. So one governs the memory kernel decay rate, and the gamma term corresponds to the strength of the non-Markovian dephasing channel. So these are the three models that we'll be using to analyze the results that we get. Okay, so we have these noise models, but what are we fitting these models to? So now I'll show the method that we have for the characterization of noise. So in our method, we use what we're calling pseudo-identity operations, which are operations that would give you the identity operation if you didn't have any noise. So for example, one simple pseudo-identity operation is just the idle qubit, because ideally, if you leave the qubit idle, you should just get the identity operation. But as I've shown you previously, and that's not always the case. Other kinds of pseudo-identity operations might involve, for example, 4 90-degree rotations about, let's say, the x-axis in the Bloch sphere. Again, if there's no noise, 4 90-degree rotations will give you 360-degree rotations, which is effectively an identity. But if you have noise, for example, in this case, if your qubit pulse is not calibrated perfectly, instead of a 90-degree operation, you might be doing a 91-degree operation. And in that case, when you do 4 of them, you effectively have a 4-degree over rotation at the end of this pseudo-identity operation. Another kind of pseudo-identity would be doing, for example, some rotation theta, and then the opposite rotation negative theta. Again, if you don't have any noise, this should just give you the identity. But because of noise, you might get some other operation. The reason why we're interested in these kinds of operations is that they amplify the error when we repeat the pseudo-identity operation. So I'll take the example of the 4 90-degree rotations. So if you have a 1-degree over rotation at each gate, you have a 4-degree over rotation at the end of your pseudo-identity operation. But now if you repeat that pseudo-identity operation multiple times, your error gets amplified. So after 1 pseudo-identity, you have a 4-degree over rotation. After 2, you have 8 degrees, and so on. Another reason why we're interested in them is that different pseudo-identities can amplify different kinds of errors. So just taking the previous example, we can have a 1-degree over rotation, which the pseudo-identity here will amplify. But you can see here, if instead of 90 degrees, we're doing 91 degrees, and if instead of minus 90, we're doing minus 91, that error will be cancelled by this pseudo-identity. So that's why using different pseudo-identities allows us to amplify different kinds of noise in the circuit. In this work, we're using pseudo-identities of the third form shown here. And the reason for that is that with this pseudo-identity, lots of errors such as over-rotations are cancelled out. So we can actually then focus on other kinds of errors such as non-Markovian errors. I'll make a point, quickly comment that physically we implement these operations by just changing the amplitude of the pre-calibrated pulses. So for example, on the device, you may only have a pulse corresponding to, let's say, a 90-degree rotation. But by just changing the amplitude of that, we can apply arbitrary rotations. So what does the full circuit that we have look like? So initially, we have the qubit in the 0 state. Then we apply a rotation axis to effectively bring the qubit to the equator of the block sphere. Then we repeatedly apply our pseudo-identity. So the big dashed line repeated n times corresponds to n applications of the pseudo-identity. And in each pseudo-identity, we apply a theta rotation 4 times. And then to apply the negative theta rotation, we use virtual Z gates. I won't get into the details of this, but effectively, by having these Z operations, we can change theta into a minus theta operation. At the end, we perform measurements in the X, Y, and Z basis to effectively perform a state tomography of the qubit. By changing this value of theta, we can effectively look at different pseudo-identities. So for example, when theta is 0, we effectively get an idle qubit. But when theta is, let's say, pi/2, what we're doing is we're repeatedly doing a 2 pi rotation followed by minus 2 pi rotation, 2 pi, minus 2 pi, and so on. So by looking at different values of theta, firstly, we're looking at different pseudo-identities, but we're also looking at how the noise changes as a function of the pulse amplitude, because we're applying different values of theta by changing the amplitude of the pulses. Now, we run these circuits on a single qubit IBM quantum device called IBM Armonk. This device is unfortunately now retired, so we can't run more experiments, but we got the data while it was still active. I showed you the value, the theta term here. So we ran the experiments for different values of theta. And we also ran it for different values of n. So we're applying different numbers of pseudo-identities. When we're running circuits on the IBM device, we send circuits for execution in batches. And because of practical constraints, there's limitations on the number of circuits we can send in one batch. Now, one issue which comes with this is that the noise can change between runs. So the time between circuits in a single batch is a lot smaller than the time between circuits in different batches. So in these set of experiments, when in one batch, we ran the circuits corresponding to one value of theta, and also the idle qubit, or the theta is equal to 0 case. And the reason for that will become more apparent later. We also ran the set of experiments over multiple days just to gather statistics and analyze how the noise changes with time. And once we collected all these results, we used nonlinear regression to fit our 3 noise models to the experimental data to see how well we can model the results that we get. Okay, let me now show you some of the results, and I'll begin with just the results with the idle qubit. So when we're preparing the qubit in some state, waiting for different amounts of times, and then measuring the qubit. I mentioned a couple of signatures of non-Markovian noise, which were multi-frequency oscillations and qubit purity oscillations. And when we got the results from our experiments, we did see these signatures. So an example of this is shown on the right here. So the x-axis in these graphs denotes the number of pseudo-identity operations that we're applying. And in the idle qubit case, this is effectively the time that we're waiting between the state preparation and the measurement. The y component denotes the x, y, and z components of the block sphere. So these are effectively the trajectory, the coordinates of the qubit in the block sphere. And in the bottom right, we have the purity of the qubit. So purity of 1 corresponds to a completely pure state, while a purity of half corresponds to a maximally mixed state. So in the top two plots, you can see that we have multi-frequency oscillations. So I forgot to mention that the crosses denote the experimental results, and the dashed line is just the interpolated results. So we didn't run the circuits corresponding to all values of n just to save on the number of circuits that we're running. So we ran the circuits for 0, pseudo-identities, 30, 60, and so on. But you can see from the dashed line that we have multi-frequency oscillations. And also in the purity of the qubit, you can see that we do indeed have oscillations. So these results show that we have a significant amount of non-Markovian noise in the qubit that we're running the experiments on. So okay, we got these results and we've now fit them to our three. So with the same example results that I showed you before. Now in these plots, the dashed lines correspond to the results of the different noise models. So the blue line corresponds to the Markovian noise model prediction, the orange one of the qubit-TLS model, and the green one of the post-Markovian master equation model. In the top two plots, you can see that the orange and green line match the data very well, but the blue line does not. And similarly, with the purity of the qubit, the blue line does not oscillate at all, while the orange and green ones can capture the purity oscillations quite well. So this is almost a sanity check because we know that a Markovian model cannot reproduce these signatures. And we've seen that the two non-Markovian models that we have do capture the signatures and can match the data very well. So this is just one result, but we can do the fitting on all of the results that we have obtained. And we do that. And in this plot, I've shown the error of the fitting, the distribution of the error of the fitting for the different noise models. So RMSE stands for the root mean squared error. And ideally, you want this to be 0. So you can see that the Markovian model has a much larger mean of the root mean squared error, while the qubit-TLS and the PMME models have a significantly lower fitting error, and also they're quite similar. And we expect this because, as I mentioned before, we can relate the parameters in these two models to each other. Now you'll notice that we don't quite reach 0 fitting error. There's still some residual fitting error. And the reason for that is that, well, firstly, our noise model is imperfect. There's errors that we haven't taken into account, such as state preparation or measurement errors, leakage errors, and so on. But also there's limited precision in the experimental data because of what's called short noise. So when we're running the circuits corresponding to each of these points, we're running them 1,024 times to average over and calculate the expectation values. That's a limit on how precise our data is. And these two together explain the discrepancy between explains this discrepancy between the model results and the ideal results. I mentioned that we run experiments repeatedly at multiple times. And this actually allows us to analyze how stable the qubit dynamics is. So in these plots, we're still just talking about the idle qubit. We plotted the sigma x expectation value of the qubit. So this is effectively the x coordinate of the qubit in the block sphere. And in each plot, the x-axis denotes the number of pseudoidentities, and all of these correspond to the same circuit where we prepare the qubit on the equator of the block sphere, let it evolve for different amounts of time, and then measure the qubit. So ideally, all these results should be the same if noise in the device stays the same. So you can see that these results were run within a span of half an hour, so from 7:52 to about 8:21. And you can see that we can get quite different results. For example, the results here look very different to the results that we get here, which again look very different to the results that we get here or here. And we can also see there's periods where the results stay pretty much the same. So these are grouped into the different colors. And then there's drastic changes and we get quite different results. So for example, between these two times, something happened and we get quite different results. Similarly, we get quite different results between 12 past 8 and 14 past 8. And these are small time scales because we're just talking about a couple of minutes. So this was quite surprising for us to see. Now, what we can do is, using the noise model, we can actually try to understand what's causing this. So when we fit our noise model, and I'll now just focus on the qubit-TLS model, we can see that the phase error parameter stays the same across the whole time span, but the qubit-TLS interaction strength parameter, so that's the orange curve, changes quite a bit. And actually, the changes occur exactly when there's massive changes in the dynamics that we see here. So what this shows is that the instability in the noise is caused by what was causing the non-Markovian noise in the device. So we can attribute the instability of the qubit to the non-Markovian noise. Now you may be wondering, why is there still such a big change? Why does the non-Markovian noise change so significantly? Well, we can't answer that question, but there's physical reasons why this may happen. And these can include, for example, the qubit-TLS model is not a complete model. The TLS will also be interacting with lots of other two-level systems or other systems. So the TLS itself can change in property. But you can also have things like cosmic rays affecting the qubits. So literally cosmic ray hitting the qubit and changing the noise properties. So in future work, we'll be looking into the reason for these rapid changes in the non-Markovian noise. But this was quite interesting for us to see. Okay, I'll now present some of the results for the driven qubit. So this is now when we're applying the pseudo-identity operations that I showed you before. I'll only be showing the results with the qubit-TLS model because the post-Markovian master equation model can't directly be used for the driven qubit because now we have a time dependence in the qubit Hamiltonian. We're working on using different master equations that we can use for this. But in these results, I'll just show the results of the qubit-TLS model. So this is a representative example where the different columns correspond to different values of theta. So effectively, these are different pseudo-identity operations being applied. The different rows correspond to the x, y, and z coordinate in the block sphere. And the colors correspond to either the Markovian model, which is shown in blue, or the qubit-TLS model, which is shown in orange. And overall, you can see that the orange line fits the data quite well, while the blue line still does not fit the data, with one exception. So now this fourth column is an exception, and that's because this corresponds to the special case where we're doing a 2-pi rotation followed by a -2-pi rotation. And that actually cancels out lots of different sources of errors. So that's why we don't really see anything happening in this case. But in general, the observation is that the qubit-TLS model can fit the results quite well, even when we're applying gates, while the Markovian model still cannot fit the results well. Just to validate this, so this was just a representative example. But if we fit the results to all our data and look at how the root mean squared error changes as a function of theta, we can see that for the Markovian model, we typically have quite a high fitting error, except for the special case that I mentioned. But the qubit-TLS model always has quite a low fitting error. So this is a good sanity check that, okay, our model can describe the experimental data very well. What we can also do is look at how the noise parameters change with theta. So effectively, we can say when we apply pulses of different strengths, does the noise caused by? Now, because of the instability that I showed a couple of slides ago, we can't directly compare the parameters of noise for different values of theta, just because the results were run at different times and the noise parameters are not guaranteed to be the same. But because in each batch of circuits, we're running the circuits corresponding to one value of theta and also the ideal qubit, we can look at the ratio of the noise parameter for the driven and ideal qubit as a function of the pulse amplitude or theta. So when we did that, what we found firstly is that we can keep the amplitude damping and dephasing noise parameters the same for the ideal and driven qubit. And we cannot keep the other two parameters, so the phase error and qubit-TLS interaction strength. We need to allow them to change for the ideal and driven qubit. And then when we plot the ratio of the noise parameter as a function of the pulse amplitude, we notice that the phase error changes quadratically with the pulse amplitude, as you can see here, while the non-Markovian noise parameter also changes, but it shows a non-monotonous change with theta. So the phase error change we can explain because of the AC Stark effect. So we have a physical motivation as to why this is occurring. But we don't so far have an explanation for the non-Markovian noise seems to be changing. So we're working on trying to model this behavior as well. Okay, I'll now conclude by saying that we've developed methods to characterize non-Markovian noise. We run experiments on superconducting qubit device, which reveal significant non-Markovianity, which can successfully be modeled by letting the qubit interact with a two-level system. We observed rapid fluctuations in the qubit dynamics, and we found that we can attribute them to the instability of non-Markovian noise. And by looking at the noise model for driven qubits, we analyzed how the noise parameters change with the pulse amplitude. These methods and results can be used to obviously learn about the noise, improve qubit control and characterization, and also implement error mitigation strategies that can cancel out this noise that we see. Sorry about that. And in I mentioned that in parallel, we're also working on the multi-qubit case. So we're developing noise models which include multi-qubit errors, as well as errors such as crosstalk. And all work that I've shown today, we submitted a preprint a few weeks ago, and I'll have a link to that in the next slide. I quickly acknowledge my co-authors, so Lachlan, Deep, Francois, and Eva. And with that, thank you for listening and for your attention. I'm happy to answer any questions.
Okay, yeah, thank you very much, Abhishek, for that very nice talk. Does anybody have any questions? I have, maybe we can start in the room and then we can check the chat. So I have a couple of questions. So in the plots where you showed how so for the idle qubit case where you showed how it changes over time between different batches.
Mm-hmm.
That was just you just showed it for the X component.
Yeah.
I'm assuming you also see it for the other components as well, right?
Exactly. We see very similar results for the Y component. The
Yeah.
Z component, because generally we just have oscillations about the Z axis, we don't see particularly interesting stuff there. There's just a decay because of amplitude damping. But yes, for the Y component, we would get very similar results.
Okay.
This slide, I also had one question on that slide. So, in this greenish areas or regimes, you actually switch off the coupling to the two-level system. So, how would those graphs look like if you kept whatever U sub ZX always at 20 kilohertz? So how would the mismatch between the data and your curve look like?
So if for this particular plot,
for these 5 greenish plots, if you kept U at 20,
we would get pretty much the results shown in blue. So like I mentioned, like the main parameter that's changing is the qubit-TLS interaction strength. The other, so I haven't shown the amplitude damping and dephasing parameters, and the reason is they don't change particularly in a particularly interesting way. But yeah, so effectively, if we kept in the green plots, if we change the qubit-TLS interaction strengths to 20, whatever, we would get the results shown in the top row effectively. Does that answer your question?
essentially, yes.
Yeah.
Thank you. In your plots of the driven qubits, right? The sigma y. You said okay for 2 pi in all 3 expectation values there are cancellations of errors. Why are there such nice cancellations for the sigma y component for pi, 2 pi, and 3 pi? Is there a simple explanation for that?
Yeah, so when we do the math, we find that for the pseudo identity, when we're doing 2 pi followed by a minus 2 pi, any error in your qubit Hamiltonian is actually cancelled out. So if you have, for example, a sigma y term, an additional sigma y term in your Hamiltonian, or an additional sigma z term in your Hamiltonian, they get cancelled out for that particular pseudo identity. I don't have physical sort of intuitive answer to that, but it's just the way the math works out that for this special case of 2 pi and minus 2 pi, you have a lot of cancellation in the errors.
But I mean, why for the y component is there also seemingly calculation for pi rotations or 3 pi rotations? Am I understanding?
Yes. So for the so for even so for pi, 2 pi, 3 pi, 4 pi, and so on, the y component error gets cancelled out, and for 2 pi, 4 pi, 6 pi, all of the errors effectively get cancelled out. I guess that's not a very satisfying answer. Maybe so for the pi case, we can effectively look at it as a change of basis operation. I realize that's not very satisfying. Sorry, I don't have a good answer for that. But just the way the math works out, that for these special cases, so we're talking about multiples of pi, there's cancellation of errors.
Thanks.
Does anybody have any questions for the other people online? Feel free to unmute yourself if you have a question. Okay, I can ask another question then. You mentioned that you're able to check if it's non-Markovian based on the fact that, so in the purity, in the idle case, you have multi-frequency oscillations in the purity, right?
Mhm.
So that just
So multi-frequency oscillations in any observable, such as sigma x, sigma y, or sigma
any observable,
yeah.
and that's just in the idle case, or is it in the driven case as well?
Yeah, okay, that's a good question. So in the driven case, when looking at the observable as a function of the number of pseudo-identities, we still expect only single frequency oscillations when we have Markovian noise. So this is a signature even in the driven case. For the purity as a signature, we find that, like, in theory, you could have purity oscillations without non-Markovian noise in the driven case. And so one example is, if you have very strong amplitude damping, you're going to go from, let's say, whatever state you have to the 0 state. Then if you apply an X gate, you go from 0 to 1. And then because of amplitude damping, you go 1 to 0 again. So in theory, it's possible to have purity oscillations. However, you cannot have purity oscillations where, like, the oscillation minimum is at 0.5. So purity oscillations of the form that we see here cannot be explained by Markovian noise.
Okay, and just also, have you maybe thought about, so there's ways that you can quantify non-Markovianity, so according to either information flow or divisibility. Would it be of interest to maybe check how the non-Markovianity changes between different batches? So, like, as you said, you can see that it changes drastically for different time slots. So you could maybe, I don't know if it would be of interest to check to see whether the non-Markovian effect changes as well.
Yeah, that'll definitely be quite interesting. I guess there's also, I guess, many different ways of measuring non-Markovianity.
Yeah.
And I know, like, papers which run experiments on qubits, they've used some measures which I think you need to prepare the qubit in multiple initial states. So I'm like, I guess one part is I'm not sure with the data that we already have if we have, like, a proper measure of non-Markovianity. But yeah, like, we can definitely run more experiments which would allow us to properly quantify it, and then we can look at it as yeah, we can use that. That would be quite interesting.
Okay. Yeah, is there any other questions? Anyone online? Feel free to unmute yourself. Okay. If there's no other questions, then I'd like to thank Abhishek again for giving us the talk. Yeah, and yeah, thank you everyone for joining, and hope you have a good afternoon. Okay, thanks again, Abhishek.
Thanks, everyone.